Alright, exercise 19. We will construct a sequence xj inductively. This is probably a good way to start a proof that tells you to construct xj inductively. So choose x1 and x such that the norm of x1 is 1. That's not hard to do. Having chosen x1 through xn, note that the set M, which is the span of x1 through xn, is closed by exercise 18b. Go watch that video if you need to clear up on that. M is proper, and that's because M is finite dimensional and X is infinite dimensional. So there is some Y which is in X but not M. So yeah, so let D for distance be the infimum over all X and M of Y minus X, which we know is strictly greater than 0, because otherwise, because if the distance is 0, then there's a sequence which converges to it, and we also know by 18 that M is closed, so yeah, so that's not good. So this is strictly greater than 0. So then choose any z and m such that y minus z is less than 2d. And certainly some such z must exist, because otherwise this infimum would not be d. It would be at least, it'd be so, if no such z exists, then the infimum would actually be at least 2d. So then we want to set xn plus 1 to be, basically we take y minus z and we normalize it. And so then clearly norm of xn plus 1 equals 1. And for every, let's say, w, and have we used lowercase m? Let's use lowercase m, because that's the lowercase of uppercase m. So we have xn plus 1 minus m. What is this? This is just by definition y minus z over y minus z minus m. And then this is equal to, I'll put it on the next line, we factor out a y minus z, which this thing is not 0. Right. Because the infimum is d, so the norm of y minus z is between d and 2d, and so it's not 0, so we can divide by it. And so then we take the stuff on the inside, and we're going to get a y minus z, and then minus, and then we have a factor of y minus z here multiplied by m. Now this all, look, this is something in m times a scalar, and z is also in m, so this whole thing is in m since m is a closed subspace. And so, let's see here, this is greater than, well, this 1 over y minus c is going to be greater than 1 over 2d, since y minus c in norm is less than 2d. And then this thing is just of the form y minus m, and we know that such things, that the infimum of all such things is d, and so this is greater than d. So this is 1 over 2d times d, which is just 1/2. So in particular, for all k less than or equal to n, xn plus 1 minus xn is going to be greater than 1/2. Hence, xj is as desired. Alright, so now we want to do part B. I don't think that this is going to fit here, but let's just start going anyway. So we want to prove that X is not locally compact. So assume for contradiction that 0 has a compact neighborhood, say K, in X. Then there is some radius r greater than 0 such that the ball B2r centered at 0 is contained in K. So then, if we divide everything by r, then if you take the ball of radius 2r and divide it by r, you're going to get the ball of radius r. So, okay, bro. So bro is contained in bar bro, and then this is contained in 1 over rk. So this means that 1 over rk contains the set of all x in X such that the norm of X is equal to 1. This inclusion, by the way, is that the closure of BR0 is the intersection of all closed sets containing BR0, and 1 over RK is such a compact set. Right, because X is nice. I know in Chapter 7 throughout all the spaces are locally compact in Hausdorff. I don't know if that's quite the case here. But anyways, in any case, 1 over RK contains the boundary of this ball BR0, which is... Oh, wait a minute. Should be... Should be B1. So why did B... No. This is... So B2R0. Okay, so here, when we divide by R, we just get the ball of radius 2 around 0. And so here, so we don't even have to worry about this whole compactness thing, because B10, or the closure of B10 is certainly contained in B20, which is contained in 1 over RK. So certainly 1 over RK contains the boundary of B10, which is the set of all x such that the norm of x is 1. Alright, by part A, 1 over RK contains a sequence xn such that, so am I using n already? It's fine. 1 over x, or sequence xn, and what's cool about this sequence? Such that for all j and k in n, the difference between xj and xk is greater than 1/2. Okay, the problem 1 greater than or equal to whatever. Well, okay, well here, 1/2 is greater than or equal to 1/2, so there we go. If that makes you happy, then it can't be that bad for you. Since scalar multiplication is, now we have to scroll. Scalar multiplication is continuous. 1 over RK is the image under a continuous map of a compact set, and thus is compact. We don't need this, but okay, so for any x in 1 over RK, the ball of radius 1/4 around x contains at most one element of set xn. And so what does that mean? Well, first of all, why is that? That's because the distance between any two elements of the sequence is greater than 1/2. And so if you have a ball of radius 1/4, you can't have two elements in there, because then their distance would be at, the distance between those two would be less than 1/2, which is not allowed. Well, if they're both on, yeah, that's enough. You could put like 1 over 5th if you want to be really safe, but I like to live on the edge, you know, because that's the edge of the ball is where you have issues. Anyway, so you have one more element of, so this of this. So thus, what does that mean? Xn is a weird sequence because it is a sequence in a compact set with no convergent subsequence. But this is a contradiction, because we know that sequences in compact sets have to have convergent subsequences. So this is a contradiction. Hence, or thus, there is no compact neighborhood of 0, and hence X is not locally compact. And this completes the proof.